In this video, we're going to talk about von Neumann computer model. So von Neumann was a mathematician and physicist and later computer scientist who was able to essentially integrate pure knowledge of mathematics and physics into computer science, and his practice yielded the computer model that to this day the major components of this model we're using in the modern hardware. So there are three main building blocks in his model: the central processing unit, the CPU, the memory, and input-output devices. And the important part of such arrangement is that the executable, both the data and executable program are located in computer memory. And the CPU is capable of executing instructions stored in computer memory by sequentially fetching them, decoding them, and then executing the steps to do the work for each instruction. So the three components are connected together using a system bus. So there are different buses in a computer, but we definitely have to recognize the address bus, the data bus, and the control bus. Most prominent items within the CPU are the registers. They can be manipulated directly by a computer program. In other words, within the CPU, we have registers, which are memory locations built directly into CPU. And when we have restrictions, for instance, on the idea that if we indicated an address of a memory location, then using this data bus right here, we're capable, for instance, load the data. A typical restriction on the CPU architecture is that only one operand of an instruction in memory can be loaded by a single instruction. So therefore, if you try to add two data already stored in memory, you need to be able to retrieve the first one, and then in your second instruction that follows it, you can then possibly either retrieve the second result and store it inside the register, or you can just use the value that's already loaded and do your addition and subtraction with another value in memory. So this is the idea of registers. Basically, they allow the CPU to store intermediate results of computations directly inside the CPU. And once again, the components here, as you can see, if we just regard this as this arrangement of using the processing unit, which contains these registers right here, and arithmetic logical unit, which is capable of performing logical functions such as and, or, and so forth, and arithmetic functions such as plus, minus. So basically taking two inputs and producing a certain output, and a set of registers. So that's your processing unit. Of course, memory can be accessed through the memory address register and memory data register. And the control unit is the finite state machine, just like we used in our traffic sign simulation of finite state machine. So this control unit essentially is controlling all of the pieces or all of the components right here, and tells these input and memory and output devices and processing unit how to coordinate the efforts to allow proper flow of all of the data from one component to another component. Collectively, this process of the data flow is called data path. Basically, the CPU data path allows us to do this. So your CPU then really it's just made up of these two parts right here. So this is our CPU right here. So everything inside this area, this is our CPU. And of course we have the memory and output devices and input devices. Of course, we recognize reading and writing memory as two different operations, and it's controlled by control unit, our finite state machine, which is built directly into the CPU by setting the write enable signal on the data bus of the memory unit right here. And of course we need to specify the address register and the data register, and then the processing unit is capable of basically getting this information in and out of memory by using this type of arrangement between all of these components of the system. So as I mentioned already, hardware units like arithmetic logic unit, registers, memory, etc. are all linked into a data path. So the flow of bits from one component to another component generally considered to be the data path design of a specific CPU. So this is an example of x86 Intel architecture data path in its 16-bit version. This is from Intel manual, this specific picture. So of course the CPU in order to perform operations has to be able to perform these steps to be able to fetch the value from memory and store the value in memory. And such memories are called RAM, random access memory. So random access memory, I think what makes random access memory, what gives it its quality, that all the values can be accessed at the same time. So regardless what is the address of the memory location in this array of cells in random access memory, the access to that specific location is the same in terms of timing, regardless what the address is. So for the entire range of memory cells right here, we can specify various addresses to indicate which cell that we want to work with to read and write the data. But the timing is exactly the same regardless which location it is. And these are the highlights for the memory address register. So memory address register is connected directly to the address bus, which connects on the other side to the CPU. And this is the only way for the CPU to communicate with the address bus. And then, as you can see, this memory address register is basically split into the high and low portions of the address specification. Both are decoded, and then a specific write enable signal is supplied into the circuitry of this RAM. And so we have this matrix of values right here that indicates addresses ranging from 00 to 33, and then of course the data register is then getting connected to a specific cell indicated by the combination of the first and the second part of the memory address register. So this is the typical circuitry, the classical circuitry for connections between memory and its address register and the data register. So the data register can be used to both reading information from memory and storing information in memory, and naturally is connected to the data bus, which is also on the other side is connected to to the CPU register for storing data, and the 1-to-1 multiplexer circuit selects input from one or the two of them. And the processing unit, or the arithmetic and logical operations unit, can perform operations such as addition, subtractions, and bitwise operations, and, or, and not between registers and memory locations indicated by the memory address register. So the size of input quantities of arithmetic logical unit is often referred to as a word length of the computer. So basically the sizes of registers and the sizes of instruction operands refer to the word length of the computer. Many processors today have length of 64-bit, I would say, is perhaps more common nowadays. Some embedded systems are still successfully relying on the 32-bit registers and CPUs. So just registers, as we begin to talk about CPU registers, they're named predefined locations for temporary storage of data while we're managing addressing modes, accessing the memory, and store intermediate results of our computations. And the good thing about von Neumann computer model, that the size of the hardware in terms of the word length of the arithmetic logic unit, so it's 16-bit or 32-bit, does not really limit the computation. It simply will take more time and more CPU cycles to compute, for instance, addition of 64-bit numbers. For instance, on a 32-bit architecture, it will take 2 separate add instructions to continue adding and accumulating the result, because we're limited to a 32-bit arithmetic logic unit structure. And if it's a 16-bit, it still can add 2 64-bit numbers, but it will require 4 adds. So you can see that this exponentially grows in terms of the data type that we're trying to operate on, and the word length that we have will yield exponentially the number of CPU cycles required to complete the same operation. Of course, you have a 64-bit machine, it just takes one addition because the CPU can immediately understand the 64-bit quantities. And so the control unit of von Neumann computer model implements the finite state machine. So it really directs all of the activity, and it is driven by a clock, and it's based on a step-by-step processing, cycle by cycle. So we call them clock cycles. So finite state machine right here basically contains the instruction register, or processor count, also known as processor counter, which basically keeps track of the next instruction in memory to execute. And the reset signal will basically reset the processing unit to its initial state. So these are the signals that control the finite state machine right here, which of course you can see that it has a control bus connecting it to all input devices, the memory, the processing unit, and the output. So we talked about these things already, and of course the finite state machine also authorizes all read-write gate control of the CPU data path. Basically, finite state machine is the control part of the entire data flow inside the CPU. input-output devices right here, like for example a hard drive, may come with their own set of commands and statuses and various data formats that the actual device can generate, indicate, and so forth. They have their own error codes and many other details, and therefore to be able to connect such device to the CPU, which is on the other side connected by system bus to the address, data, and control bus on this side of the diagram, we use input-output controllers. So basically, controllers allow to connect the system bus with the internal electrical signal interface to an actual physical device, such as our hard drive, for example. So when the CPU is connected to memory, right, so this is our memory and this is our CPU right here, and it's connected by this data bus, which is of course the data bus, the address bus, and the control bus. When we have this connection between the CPU and memory, we can make the input-output devices, various types of input-output devices. We could map them to a certain area of memory. We can map their connections to a certain part of memory. And when it's done like this, the CPU could be reading and writing information into these memory locations already mapped into certain devices. So this is called memory mapped input-output. Another possibility is to use an isolated input-output address space. What it means is that when we have a memory mapped input-output, the same CPU commands that work with memory locations are available to work when communicating with devices. In cases of an isolated I/O, what happens is that we have basically a separate memory space apart from our RAM, random access memory, and we have a dedicated separate bus that connects the CPU with this separate address space right here, which is now mapped to these physical input-output devices. And so these memory locations live in memory space that is separate from random access memory. What it means that now the CPU provides a separate set of instructions which will use these separate address space, which is typically called an input-output address space. Okay, so these input-output ports that physically communicate information to the device can then be communicated with a separate set of CPU commands. So these are these two versions of mapping physical devices into the memory space that the CPU can access by using its commands.